All right, so today we have a presentation on lasers. Their introductory presentation, but feel free to stop me for questions anytime you would like. And first, I'd like to start with the applications of lasers that we see all around us. And for this, I would like to ask you guys what applications of lasers you can think of that you know from everyday life, or maybe not so everyday life. Yeah.
Like in construction when they're making level stuff.
Oh, right, for like measuring. Yeah, that's right. That's a good one. Yeah.
The energy break even or something up with Lawrence Livermore National Labs like a couple of years back.
Okay, I didn't hear the first thing you said.
It's like the Lawrence Livermore National Labs, the energy break even thing. They like through fusion? Yeah, for fusion. Yeah.
Oh, okay. Yeah. So in science, yeah, for sure. Yeah, no.
LIGO, it's like the, I don't know what you're saying.
Okay, yeah.
I was gonna say, yeah, it's like the
Gravitational wave detection. Yeah.
Yeah.
Yeah, very nice. What, we have time for one more, I think, but no worries. Yeah.
Like surgery.
Yeah, very nice. So you've already mentioned a few of the ones that I put on this slide. So we have the industry, because lasers are very, very precise and still very powerful. You can do things like engraving or even cutting through really hard materials. We have the applications to medicine, like surgery. Something we haven't talked about yet is communication technologies. So for your home TV or internet signal, that can be transmitted through a fiber, where the laser light is transmitted through the fiber by total internal reflection, which is really cool. We have defense and like geospatial awareness. So this is a schematic picture in the bottom middle of a LiDAR technology, which uses some kind of flying object that shoots lasers down at some kind of area it wants to scan. And by calculating or by detecting how much time it takes for the signal to come back to the source, you can calculate back how high the object is that you scan, and you can get really detailed landscapes from that. We've talked about the science applications of this, as you can see in the top right, and you've also mentioned gravitational wave detectors. And then even in entertainment, such as laser shows, you see lasers. So they're really everywhere around us. And that obviously raises the question, why? So what makes the laser such a powerful tool that we can use in so many applications? And the answer to that is the keyword coherence. And I'm going to spend a couple minutes dwelling on this concept because I think it is very useful, but also maybe not the most intuitive to understand in the first place. So firstly, I changed this font to white, but it always changes it back to black. So let's start by saying, as you may know, we can describe light with waves, and those waves have a certain energy. Does someone know by chance what the energy of the photon can be expressed as? Yeah.
H bar.
Yeah, wait, oh, you mean you?
You, yes, sorry.
Yeah, no worries, that's exactly right. So this is exactly that, or you can also likewise do that express that in terms of the wavelength. Sorry, I changed it just before the presentation. So if you can't see, this just says HC over lambda, where lambda is the wavelength. And in the simplest model, a light wave can be described by a sine or cosine function, which is also covered by this. But in general, you just have an electromagnetic field is an amplitude, and then cosine omega t plus phi, where omega is frequency and phi is the phase. And the phase accounts for phenomena like interference, as I'm sure many of you have already heard about. But just to remind everyone, you have constructive interference is the phase of two waves overlap. So that means they're maxima and minima at the same place. Whereas when they're exactly opposed to each other, you get destructive interference and they cancel out. So now that I've gone a little bit into that, we can talk about what coherence is. And in fancy words, you say it is the correlation of the phase of light waves. Or I like to put it in simpler terms, it's how much a wave resembles itself. So there's two notions to this. Namely, there's temporal and there's spatial coherence. And looking at this top two graphs or graphics of this image, this is temporal coherence versus incoherence. Namely, I wrote this down so I don't butcher it, but for temporal coherence, which you see here, is the correlation of phase at different points in time. So you might, I think a good way to describe it is envision that you're standing somewhere and then the signal passes by you, and then I don't know, a second later, sometime later, you compare that signal with the signal that passed by you a little bit earlier. So you're comparing to the same signal at 2 points in time, and you're asking yourself, how predictable is the phase at this later point in time? And so imagine if you have this really nice oscillation that is just one frequency, we can, I think, pretty well predict what that wave is going to look like a little while later, because we can easily just check how many oscillations fit in this time that has passed and keep track of the phase. So that is temporally coherent. Whereas in this example, that is temporally incoherent. The signal is very noisy. It's going to be really hard for us to predict what the phase is going to be like at a later point in time, just by knowing the signal at one point in time. So it also is kind of a measure of how monochromatic is the signal. And monochromatic means like one color is kind of the translation of that. So the wavelength corresponds to a color in that sense. So that is temporal coherence. Just a reminder, that is the correlation of phase at different points in time. Now, spatial coherence, as I'm sure many of you might have guessed already, is the correlation of phase at different points in space. So up here, we looked at the signal over time. Now down here, we look at the signal over in the space X, Z plane. And just like in a pond where you throw a stone in the water, imagine we do that here at the origin. The wave fronts, which mark those maxima of these oscillations, propagate outwards radially. And this is a very nice example. The wavefronts are all aligned, they're really nicely shaped. It's easy to say, if you're here, where is my wavefront at a different point in space? But on the other side, this is the spatially incoherent signal. The wavefronts are kind of wonky. I think it might not show up the best on this presentation, but they're kind of wonky. They're not really nice and related to each other. So it's hard to say where is the wavefront going to be at some other place in space. And that is what I mean by it resembles itself. It's kind of like how predictable is your signal. So I realize this is a pretty heavy concept. So don't worry if you don't feel like you've had this enlightenment just yet. But are there any questions until now? Yeah.
Maybe I didn't fully understand what you were talking about, the monochromatic aspects. Like, were you saying that was related to this correlation?
Yes. So I said temporal coherence is a measure of how monochromatic your signal is. So here we have one wavelength, and as I'm sure many of you know, the wavelength corresponds to a certain color, which is what I meant by monochromatic. So whereas in this, and you can view this as a superposition of different waves of different frequencies. So there's different contributions to the signal, which means that it is not monochromatic. Yeah.
So does that mean that So do the waves have to be evenly spaced apart between? Is that what you mean by phase? Is that, are you measuring like how, like the time between each?
Yeah,
Like,
yeah.
hit?
The wavefronts, or yeah, exactly. The wavefronts are evenly spaced. Yeah. So now I've explained this in detail and why. It's mainly that lasers are both spatially and temporally coherent, which makes them special. If we compare this with just like a regular light bulb, for example, I think this illustrates really nicely what happens. A regular light bulb or light source that we see in everyday life is a superposition of these different colors. So different light rays with different wavelengths or equal frequencies. And so they're not temporally coherent. And they're also not spatially coherent because the light bulb just sends out these light rays in all kinds of random directions at random times. And so they overlap. And this is not really useful for you in a lab environment. Yeah, great. That's what I wanted to say about coherence. And now that I told you that laser light is coherent, the question naturally arises, why? So, and that lies in how laser light is generated. And the answer to that kind of is hidden in the name itself. So laser is actually an acronym for light amplification by stimulated emission of radiation, which sounds a little bit long. And the key concept that we were going to try to understand is the stimulated emission part of this. For this, we're going to take a little bit of a deeper dive into light-atom interaction. And a key concept in quantum physics is the wave-particle duality. As I reckon maybe some of you have heard already, or by show of hands, who has heard of wave-particle duality? Okay, cool. Why am I even here? Yeah, the key point is you can express quantum particles both in terms of a wave as well as in terms of a particle. And that also counts for electrons. So we assign those electrons a characteristic wavelength that we call the de Broglie wavelength. And this solidifies the key idea of Bohr's atom model. Before Bohr proposed his model, there was Rutherford's atom model, which was mainly you have a positively charged nucleus, and you have electrons that are negatively charged around it on circular orbits. However, those orbits could have any energy as long as they were stable. Now, Bohr extended this model to that atoms have discrete energy levels for their electrons. And those energy levels are given in his model by this equation that their radius is always a multiple of the de Broglie wavelength of those electrons. You can kind of understand this as when this condition is met, an electron orbit is actually just a standing wave of an electron because it's de Broglie wavelength, it's kind of circles back and then connects smoothly. So it's like a constructive interference in that sense. Of course, we know today that this isn't the whole picture. And if we actually want to describe atoms in full, we still need to solve the Schrödinger equation. But this is the very basic and nice visualization of why we describe atoms with discrete electronic energy levels. And that's the main takeaway that I want you guys to remember from this slide. In this bottom picture, I've just briefly drawn how we're going to look at those two-level systems. And we usually draw the top line and the bottom line. E1 is the ground state, E2 is the excited state, and they have a certain energy difference that we can describe by H, like we've already worked on the board earlier. So we've talked about, oh yeah.
Quick question. So the energy level spacings, do they necessarily have to have like equally spaced? Because by using the equation equals HV, you're implying that all electrons have like a specific energy spacing. You go from one spacing to the next, right? But that's not.
Yeah, that's not the reality.
So we're just making an assumption.
Yeah, we're always gonna look at two energy levels and call their energy difference H nu. But in reality, atoms and all those kind of systems have much, much more energy levels. And we are only always looking at two distinct ones that are practically used for our cases. Yeah. Yeah, good question. Otherwise, you would definitely like label that if you had multiple. Yeah.
So you're saying this is kind of like a generalized model, like it's not any one energy. Is that what, am I understanding that right?
Yeah, I'm just talking about, imagine a random atom. It doesn't have to be anything specific, but say we take the hydrogen atom where like the energy, I think it's like 1/n scales as like 1/n squared. And then you have like these energy levels and they're not equally spaced, they're quadratically spaced. But we always look at some kind of transition that we want, say these two, and then we call that E2 and E1, and we only look at this transition even where there's more to it. Yeah, good questions. So now we know we have light and we have an atom that we model as a two-level system. How do those interact? There are three key processes, three things that can happen. Does anyone have an idea of what can happen when a photon comes into this two-level system? No worries, not, but yeah, did you have an idea?
Do you mean like sense of like getting forward and stuff?
Yeah, exactly. Yeah, very good. Does somebody else want to add to that? Yeah.
Decrease the amount of energy to go from one energy level to or is that?
I'm not sure, maybe?
Are you saying like emission of a photon?
That is what I meant to get at, but I'm
Oh.
also trying to understand what.
I think I was thinking about that.
Okay,
Because you're saying decrease of energy,
Yeah.
like of the atom. Yeah.
Oh, right.
yeah, great. So these are the two like obvious interaction types. We talked about absorption, meaning we have a photon coming in and our system is in the ground state. And this photon gets absorbed and that energy package is used so that the atom gets excited. The other way around can also happen that when our system is already in the excited state, it drops back down to the ground state, it releases this energy H nu, and the photon gets sent out. And then there's another process that can happen, which is spontaneous emission, namely when the system is in the excited state and it just randomly drops back into the ground state and emits a photon without the photon coming in to stimulate that. And these processes all happen at the same time and overlay each other and are balanced out in thermal equilibrium. A key thing to note here is that those stimulated processes are coherent processes. That means specifically looking at stimulated emission, that photon that gets set out has exactly the same wavelength, propagation direction, and phase as the incoming photon that stimulated this process, which you can, I think, nicely see by the way how they drew those waves, that they're actually nicely overlapping and all propagating into the same direction to the right here. So keep that in mind. Stimulated, oh, yeah.
I was just saying, like, how exactly does stimulated emission work? Like, how do you like send in like photons, for example, and that stimulates like excited photon to spit another one out, like.
Yeah, that's a good question. I've always kind of wondered what's going on myself. I think I'm not sure if there is a nice intuition to this or if it's just something that like this is a very like macroscopic description of light atom interaction. And I think you can take a deeper dive into like Maxwell's equation and I think the math will tell you what's going on. But in terms of like I think absorption is more intuitive than emission for sure. So sorry, I don't think I can give you more intuitive understanding of that right now. Yeah.
Yeah, so when you said, like, for spontaneous emission, when you said randomly, is it quite literally random, like probabilistically random?
I
Or
think
is
so,
it-
yeah.
okay.
It adds noise to your
Okay.
system, yeah. The only thing that's not random is this energy difference. The photon that is always this h nu,
Right,
yeah.
yeah.
But the direction and the phase is random. Yeah,
So how do you distinguish between like stimulated emission and spontaneous emission? Would you have to like look at the probability of like how often photons get emitted from your atom to like kind of discern whether it's like stimulated or spontaneous? Because obviously like stimulated is like you send out like beams to like make the emission happen, like how do you know that what you're doing is working, for example, and that's not
you mean like in the
spontaneous?
lab environment?
Yeah, that's what I meant.
I think the one thing would probably be this like, that you can probably distinguish. Is see a difference between the emission that is a signal and the spontaneous emission that is more noise. So, if you look at the spectral density of the signal, I think the spontaneous emission would kind of show up as like a swirly noise line, whereas the simulated emission would not be that. I'm not sure if people actually go in the lab and be like, oh, we're gonna find out today whether our atoms are doing simulated emission or spontaneous emission. Like it both happens. And you can't really avoid that happens. So it's the light is just gonna come out of the system like it is. Okay, yeah.
So considering this hypothetical experiment where we're firing like a beam of light at this atom, and we don't know if it's spontaneous or stimulated. So like, would it just be like this? The stimulated emission would be like a higher intensity or something than like the spontaneous, maybe.
Possibly,
Yeah, I mean,
yeah,
if it's not like a real experiment, and like,
yeah.
why does it matter?
Yeah, I think that's all I can say about that right now. Yeah. All right, so we know stimulated emission is very important, and now that we've gone through all the basics, we can finally take a deeper look at what is the laser actually comprised of. So I've just copied in this picture of the stimulated emission as like help to remember. And the laser consists of three main constituents. I know the image labels 5, but in general, you have first a gain medium, which is symbolized by this green block in that diagram. And that can be anything from like a crystal to a liquid to a gas, whichever medium you choose. And that is where this stimulated emission happens. And secondly, we need what is called a pump source. So to say that to have stimulated emission, we need our system originally to be in the excited state. But naturally, the system always prefers the lower energy state. That is due to the Boltzmann distribution. I've put it on here just because I think it's going to appear in some kind of physics class at some point, and it's nice to just have seen it already. So the probability for the whole system to be in the state labeled I is proportional to the exponential of minus the energy of that state by KT, and K is just the Boltzmann constant. So that tells you if we have a higher energy state, that will be less preferred. So the pump source is used to contradict this effect and to get more electrons, more atoms into the excited state. And this pump source can be anything from like an electrical voltage that is usually used for gas lasers, a flash lamp, or even like a smaller laser that drives this transition. That is what we call population inversion, is when there are more electrons, more atoms in the excited state than in the ground state. And I've put a little asterisk here because I did not want to leave without just saying this. We're always looking at 2-level systems, But in reality, to achieve population inversion, you always need at least a three-level system. You can prove that by looking at the rate equations of these light atom interaction processes, which I'm not going to go into today. But yeah, that is the physical reality of things. Still, we're going to look at our two-level system. So we have the gain medium and the pump source as the two main components of the laser. And the third one is what is usually called a cavity. And that's nothing else but just two mirrors at both ends of this gain medium. So we know that this pump source excites our atoms in the gain medium. And this way, stimulated emission can happen. So a photon comes out, and that photon can travel to the next atom and then generate more stimulated emission. So we generate more and more photons that are all coherent because stimulated emission is a coherent process. And the nice thing about this cavity is that then the light gets reflected back and forth. And so that kind of creates this snowball effect of more and more photons being released. Now, how do we make sure that they don't do disruptive interference and everything just cancels out? For that, we make sure our cavity length matches the wavelength of the laser light that we want to produce. So 2L is where L is the length of the gain medium, is just one time where photon travels both directions, and that has to be a multiple of the wavelength in order for this to happen. I kind of illustrated that with this picture up there. So you always try to aim to tune your cavity so that the wavelength you desire will be supported by constructive interference. And now we have this light field building up between those two mirrors. How are we going to get it out of the system? How do we generate this laser beam? And for that, one of the mirrors is made just ever so slightly transmissive to this light. So I think in like rotational wave detector or something, you have something like a reflectivity of 99.999% or something, and then just the smallest percentage of the light that's in this cavity gets out. But because we have this insane buildup in the gain medium, this very small percentage is enough to drive this powerful laser beam. I think this is all I wanted to say about this laser setup. Are there any questions about this? Yeah.
If it's a snowball effect, then how do you get it to stop? That's
a good question. I would assume if you were to stop pumping, that this effect might swing back to this thermal equilibrium state, and the system might eventually relax. Or you can, of course, just you can couple out some of the light and just make it go out of the system, or make the mirrors less reflective or something, so you get more losses. But yeah, I don't think I've ever really thought about how you want to actively stop the laser. Another question about these three main components of the laser. All right. So, dang it, I don't know why it's showing in black font. Oh well. One of the things I also wanted to talk about is the resonator itself. So by that I refer to this cavity, these two mirrors that are facing each other. And their curvature and their distance also highly influences how stable this resonator is, meaning how well the light circulates back and forth in this resonator. There's a stability criterion, which I'm going to copy on the board if it's not showing up here. So each mirror gets assigned a constant G, and that is 1 minus the distance between the two mirrors over the individual mirror radius of curvature. So you can think of a totally plain mirror, something like this. This has a curvature of infinity, and that like a curvature radius of infinity, because if you have light coming in, it'll always reflect that back. And it will, those two light beams will never meet, they meet at infinity. If you have a more convex mirror, something like this, then those light rays would meet here, and then the distance, this distance will then be called this radius of curvature. We assign this G to each mirror, and their product needs to be less or equal to 1 for this resonator to be stable. So as in the plane parallel resonator, where both mirrors are just exactly plane, which is also called a Fabry-Perot cavity. You might hear that like Fabry-Perot interferometer, so you know that's that. I think it's obvious that G1 is G2 because both mirrors are the same. And I've originally written here that R1 equals R2 equals infinity in this case. So I guess it's not super clean math, but in that sense, it's 1, if you want to calculate G, that is 1 minus a finite distance L over infinity. So you kind of treat this term as 0. So G for both of those mirrors would equal 1. So their product is 1. And then that means the mirror constellation is stable. Is that clear? Did I write that down? Okay. Yeah, sorry about that. I don't know. I think sometimes when I save the PowerPoint, it always says some things are not compatible, and I think that might be it. Oh, never mind. There it is. I just had this animation going on. So yeah, this is just a summary of what I just said. So I'm not going to go over that again, but it's going to be in the slides if you want to look back at it. Then I've also briefly touched on this earlier, but there are different types of lasers. They get characterized in terms of what their medium is. So there's gas lasers, such as helium neon lasers or CO2 lasers. There's the solid state laser. One very popular one is what is called the ND-GAC laser. That's neodymium doped deuterium aluminum garnet. And no, I did not learn that for this presentation today. And that's a very famous, one of the red lasers that you see in pretty much every lab, which is this one. Lasers at 1064 nanometers. That's a very popular one because it's very stable and nice to handle. And then you can have other mediums such as dye laser, diode lasers, which use a p-n junction and generate light that way. And some lasers, as you may see, like the titan sapphire one, it has a broad spectrum. So this is actually a tunable laser, which is pretty cool. So as you can see, but for this laser specifically, you can adjust the temperature, and that makes the laser emit at a different wavelength. So there's all kinds of cool stuff going on with lasers, and there's a bunch of them. This is probably just a small portion of all the ones you can build, but just, yeah.
Where did you say was the adjustable one? Or like one where you like change the temperature, like changes?
That's the titanium sapphire one, and that's a solid state laser. Yeah, and I think there's another one down here, but I'm not too familiar with those. I always know when I took the lecture on coherent optics, my professor was always emphasizing the titanium sapphire one is the laser because you can do so much with it. Yeah, so I thought it would be fun now that we have all this knowledge, we can look at what's actually inside of our usual laser pointer. This is kind of to be read from top to bottom. So top is what the laser pointer looks like from the outside. Then one layer down, you see a little bit of a close-up view. And what's really interesting is this BPSS laser module, and I wrote down what that means somewhere. Oh yeah, diode pumped solid state laser. So we're essentially, this is only, we're looking at this unit. And this laser is a solid state laser. We use this material, neodymium doped yttrium vanadate. And we have as a pump a smaller laser, which is a diode laser. So this diode laser is powered by an electrical circuit, which is what we need the batteries for. And then this pump laser emits pump light to our main, oh, sorry, this is the focusing to our main gain medium, which is here. So this is where the stimulated emission happens. This is where the light field builds up. And there are two mirrors. The two resonator mirrors are here and here. So this is where the light travels. KTP just stands for potassium titanol phosphate. And that is used for frequency doubling, which means we essentially just half the wavelength. We make green light out of red light. That's a nonlinear crystal effect, which is widely used, but that is definitely more advanced. And I haven't even taken a class on it, so I couldn't tell you how that works. But this KTP is a type of crystal that has this effect that if you shine light in a certain way, it doubles the frequency of the light. But yeah, the main laser medium here is this neodymium doped yttrium vanadate, which is right here. And yeah, so now this is where the main lasing happens, and then this green beam will come out. We have another collimator just to make sure it's nice and parallel and precise, and an infrared filter to filter out any possibly remaining red light that has gone through this KTP. Yeah, I think that is all about this diagram. Are there questions about this laser pointer? Yeah.
Said this KCP halves the wavelength, but the bottom it's only goes from 800 to 500, right?
Oh.
Maybe not.
It's interesting because I would have expected 1064. Usually you see NDAC is 1064, and then that is half to 532. Yeah, that's a good question. I'm not sure what that's about.
Yeah.
Might be like a two-step
Yeah.
process.
That could be. Yeah.
I have maybe another addition.
Oh.
You said that this is actually a 3-level system.
Oh.
So I think maybe
Well, sorry, 3-level system or more, but yeah.
more. So maybe like I don't know, one of these intermediate light wavelengths is like you have to excite your atoms up to the like third level, like from the ground state to like the third level, and then they like maybe spontaneously drop down to like the next level.
Yeah.
And then when they drop down back to the ground level, that's the green. Does that kind of make sense? Like you have these different
that
maybe
concept
something?
is definitely true for 3-level systems. That's how that works. I'm not sure how this nonlinear crystal works. So,
Okay.
yeah.
Maybe it like enhances that effect or something.
I don't know. I think it has something to do with polarization, but yeah.
So this is kind of like a tangent, but this laser specifically would just produce one color. If for lasers where there's like multiple different colors that are being produced, would you change the IR filter, or would you just change that MCA, like where like it shifts it from like the 800 the red light to like greenish light?
Yeah, you mean if there's like residual light that we don't want of like a different color, or
Well, like there's lasers of different colors, right? Not just like
yeah.
rates. Like if they wanting to change their color, does that mean that you're changing the actual filter, or like?
Oh, I see. I think the minority of the lasers are tunable, so that means only the minority of lasers we can actually do that and like continuously, alter the frequency. So I'm not sure if you can just do that with this, because the laser frequency is very much determined by the gain medium and its atomic properties. So usually, maybe you could, because this is a crystal, right? And you could use things like piezoelectric effect or something to tune it a little bit. But I'm not sure how feasible that is for most lasers. If you do want to tune the lasers, I'd suggest you take a material that actually supports that, like the titanium sapphire one. Yeah. Wow, we're already approaching the end here. I just briefly summarize what we've learned today with this funny cat meme to get everyone's attention back in case it was too boring. So we've learned that lasers are pretty much everywhere around us. And that is because they're sources of coherent light, both temporal and spatial, making them really precise and powerful. The laser consists of the three key parts, namely the gain medium, the pump, and the resonator, also called cavity. And it works by light that is amplified due to the stimulated emission that then constructively interferes with itself. The geometry of those resonator mirrors is really important for the laser to be stable. So that means not to have too much loss of light that gets like shined out of the system. And we have different laser types, many of them that are classified by the gain medium type. For example, gas lasers, guide lasers, you name it. Yeah, so this is an exercise we can do, but before that, do we have any questions about what we've learned today? All right, now we have about, yeah.
Another question, for the lasers that like can actually like maybe like there's like a difference between like a laser that can be just used to point, like the ones that actually are able to like cut through stuff. Is that just like a result of like the beam and like how many like electrons or photons are shooting through that, or is it like more of like the wavelength of the frequency?
That is very much like a difference in the power or like intensity of the laser.
So that's more the gain medium kind of thing, how many electrons you're shooting through that.
So those industry lasers are usually gas lasers, like CO2 lasers or helium lasers. So they're also more heavy duty, I would say, and they're not as like portable like a laser pointer would be. So you really
power
need,
source would be
you need a big pump unit, you need a cooling unit. And so I think you only find them in this like heavy duty machinery. But that also accounts for, I've actually written it down, the gas lasers produce like tens of kilowatts, but the laser pointer is just 5 milliwatts. So you can see the difference in the order of magnitude there. Yeah, so I've prepared this exercise. I think we can start and just see how many you get. This is on the resonators. So I've written down some reflectivity is wrong. Some radii of curvature, like we've seen over there on the chalkboard. This is R, and this says R1, this says R2, in case you can't read it. I've written down different parents of those. And if you'd like, I would like you to like figure out what does this geometry look like draw it, so something like this. And then also check if they fulfill this stability criterion, which is this one that I've written over here. So just as an example, we've already talked about this plane parallel resonator, which I think I can give away, and we've talked about before, is case 5 here. So we take R1 equals infinity, R2 equals infinity, plug that into our handy equation, and see that it is in fact stable. But that may not be true for the other examples that I've written down. So yeah, if you'd like, go ahead and give it a shot. And yeah, is the exercise clear? Okay. Yeah.
What was the actually sorry.
Okay. Yeah.
About like on the previous slides, like when you were talking about like the isolation level, like small portion of the beam, right, for like actual use, they take out a system, like how does that work again?
You mean how part of the beam gets coupled out from the system? That works by that the reflectivity of the mirror is never a true 100%. There's always going to be a very, very slight loss in reflectivity. So we use this special mirror that transmits some type, it's a very small percentage of the light. Yeah.
Wait, so does that happen like every time the light hits that mirror? So
Yeah.
mirror?
Mhm.
Okay. Thank you.
Yeah. And let me know if you'd like to do one together or something, but I'm just gonna give you a couple minutes to think about it. But the solutions are supposed to look something like this. I've just labeled those examples 1 through 7, like we had on the previous slide. This is also how you draw those diagrams that can be nicely sorted into the stability diagram. So everything that is in this blue area is stable, and everything that's on the line is also still stable, but just by a little bit. And I made up my own example, which was number 7, which is outside of this region. Where you can see one of the mirrors is convex and one is concave, but the concave one is too concave in that sense that it reflects too much light out of the system. So the loss is too big to actually blaze. Yeah. So nice job, everyone. I wanted to show this video, but I have it on my personal laptop and not on the laptop that I had to use as an emergency. So unfortunately, I can't show it now. I can show it on my phone for whoever wants to stick around. But yeah, that concludes my session for today. Question?
Can you talk about that? Looks like just back to the graph.
To this one? Yeah. This is just if you Google like resonator stability diagram, this exact image will pop up.
How do you read that? Like 0, 1, 1, 1, like.
Yeah, so this coordinate system is G1 versus G2. So the first entry will always be G1 and the second entry will be G2. So you always multiply those numbers together to look if they fulfill the stability criterion. And because this is 1 over x, you can see why like all the mirrors whose G values as a product equal 1 are on this diagonal, like the plane parallel, or also the concentric one. But everything that's kind of like not a nice number, like 1 or 0, will just be somewhere in between. Does that make more sense?
Yeah, how do the G values specifically correlate to the path that is shown in the diagram?
Yeah, so like I said, for example, this R is the curvature radius, so where two light beams would meet. So if we were to look at maybe not the planar, but just like a convex mirror, or something like this, and say this distance is L, and then two light beams would be reflected at exactly this distance, then this curvature radius would just be L. Whereas when, for example, they meet pretty sooner, somewhere around here, then R would be L over 2. And that's how you can kind of trace that back to these diagrams. Like for the concentric mirror, R would be L over 2 in both cases. And if you plug that in, like we've done here before, we see that G equals -1.
Yeah.
So that's when we say that the plane parallel is infinite.
Right.
Because
Because those beams would never meet.
yeah,
So we say they meet at infinity, which is obviously not a phonetically super nice representation because you don't really want to divide by infinity, but for our purposes, that works.
so what do we call the G? There's a specific name, right? I know
I actually,
the inequality is called
the stability criteria, yeah. I actually don't know of a certain name for that, to be honest. That could just be me, but when I did my research on preparing this, I didn't find anything. Question?
Oh yeah, I was saying also there's a way that it's calculated, like you can always go like backwards from your coordinate system as well. Because like for 2, I think you need a value of -L over 2 for your r distance, and that would only happen if you extend that diagram to the left.
Right, exactly. That's how you get those negative.
Oh,
Yeah,
So the only way that it could ever like be infinite if it's like perfectly parallel.
yes,
Okay,
yeah,
that makes sense.
yeah.
So it's like a negative radius mean it's concave.
I think so, yeah, that's what, yeah. You could probably also choose the other convention around and like just switch and say convex is negative, but this is just you just stick to one convention and then, yeah, one of the mirror types will be plus and one will be minus. More questions? Well, then thanks again, and thanks for all the questions and for your participation and making it out here on this snowy day. It was my pleasure to talk about this. I hope you learned something. Yeah, even if it's just a little bit, and yeah, hope you guys have fun. Yeah.
So I guess going back to fast growth. Previously, like about the small beam lightning out, right? The laser setup, like is there like a lot of heat buildup in like the mirrors, like
And what?
in the mirrors that you're using to like bounce the laser back and forth?
Yeah, there's generally a lot of heat buildup in the cavity, which is one of the main restrictions when building a laser. So you really need great cooling systems. And I'm not exactly sure how that translates to the mirrors, because after all, they do reflect all radiation pretty much. But the mirrors are definitely a crucial part to consider in terms of like even like photon noise, like when it hits the mirror, it moves the mirrors, these kind of things. The mirrors are a very intricate part, and you want them to be as stable of a factor as possible in your system to get a really stable laser.